Okay. Okay. Today's we will start this session with talk by Madhavan. Okay. Just by way of introduction, Madhavan was actually a student at the university. I am a faculty member, so I have known him since he was knee high to a grasshopper, very tiny. Now he is a professor at RRI. Okay. And his main research interests are, I think, basketball, where he has twisted his ankle, and hockey. So he is quite fit to face this audience. Okay? And he has promised us to tell about black hole evaporation, and the promise is even deeper, that if he cannot dazzle you with his brilliance, he will baffle you with his bullshit. So here is Bhaskar.
Okay, so first, thank you for the very kind introduction. And you can tell that some of it was fictional because of especially the height issue. Bal, as is well known, no, he has been described in a talk which was introduced by ECG Sudarshan as Balachandran is the best physicist per unit length that I know. So I'd like to thank TRG, Shyam, and everyone for inviting me and giving me an opportunity to speak here. So this is the title of my talk, Black Hole Evaporation from the Perspective of Quantum Gravity. And let me first say a little bit about the words in the title. And let me start with quantum gravity. So the problem of quantum gravity is to construct a consistent quantum mechanical description of the gravitational field. And the gravitational field in its classical form is best described by Einstein's theory of general relativity, which reinterprets the gravitational force in terms of the geometry of spacetime, specifically its curvature. So any theory of quantum gravity is also a theory, as emphasized by Paddy, also a theory of spacetime geometry. It's some quantum geometry theory. When does a theory of quantum gravity become important? That also, I think, Saurya talked about that. So what one can estimate through just some very naive dimensional analysis, not even dimensional, just take the constants of the theory. So general relativity is characterized by Newton's constant and the velocity of light, and then quantum mechanics by h bar. And so if you combine these things together, you get something of the dimensions of energy, which is called the Planck energy, 10 to the 19 GeV or so. And this is where you expect that quantum gravity effects are going to become important. And of course, no accelerators are going to probe this energy. And it is very hard to make any experimental predictions which are accessible right now, except some very crude ones. So it's a legitimate question as to, why should one do this activity? And at least my answer to it is that if there were several complete consistent theories of quantum gravity and all of them differed in predictions only at the Planck energy, then of course one should not be doing this activity. But the fact of the matter is that one does not have even a single complete satisfactory theory of quantum gravity. So it is something which is a challenge and which is good to do, with all the caveats which Professor Kulkarni mentioned earlier, and which I don't know whether I fit those or not. So given the fact that it's going to be hard to find direct experimental signatures, even though people are trying, as you heard in the last talk, what one can do is look for points of theoretical tension. So one can take theories which we know, quantum field theory on a given space-time, classical gravity, and try and put them together and force them together and see if one generates any tension, which can then point towards a resolution by any putative theory of quantum gravity and maybe give us hints as to how to construct such a theory. So one focal point of this tension, and perhaps the most important or striking one, is in the context or in the stage in which you try to analyze what happens to the behavior of quantum fields on a fixed spacetime geometry. So in other words, you have a classical gravitational field but a quantum matter field, and you're in a domain which is pretty physically well motivated and robust, where fluctuations of the gravitational field are not important. And when one does this, so this is what Hawking did, you find this strange phenomena that while black holes do not radiate classically, they actually radiate quantum mechanically, and they start evaporating. And so this leads to a certain paradox, which I'm going to come to now. And one would like to see and sort of understand whether there's any way around this paradox and what possible properties of quantum theory of gravity would do to maybe sidestep this paradox, or et cetera, et cetera. So the plan of my talk is going to be as follows. Okay, I was told if I press this button, it is going to move, but it doesn't. What do I do? Just should I press return or something? No. Just press. Okay, so what I'm going to do is I'll first describe exactly the work I referred to, which is Hawking's picture of how a black hole evaporates and the ensuing so-called information loss problem. Then I will try to describe some ideas which were put forward by Ashtekar and Bojewald, which are predicated on the idea that the classical singularities of GR are going to be resolved or are not going to be obstructions in a quantum theory of gravity. So with this view, if one looks at the evaporation process, one arrives at a slightly different picture as to how the evaporation process may proceed, and I'll describe that a little bit. Now this is all very qualitative. It's more like a paradigm or a proposal as to how things could go, and so one would like to be a little bit more detailed and quantitative. And 4-dimensional GR is too hard even classically, and we don't have any theory of quantum gravity. So one thing to do is to look at technically simpler models which share many of the features of the problem of interest, and this is supplied by these 2-dimensional black holes. And so I will go on to a detailed analysis of 2-dimensional black holes, and we'll see what happens over there. So the first two parts are, I'll go a little slowly, and the last part anyway is technical, so I'll probably have to accelerate a bit, but I think the first two parts themselves would be of interest, at least to people who haven't seen them before. So let me first come to, before going to the Hawking thing, which has quantum fields on some classical background, let's just go back to the classical black hole. And in previous talks, you've seen these figures of classical black holes, which are more physical, where the light cones are tipping over, etc. So I've given a different representation of the same geometry, and this is maybe invented by Penrose, I'm not sure, but it's called a Penrose diagram. And what I have on the left is, so what do you do in a Penrose diagram? So I'm going to be talking on the left about spherically symmetric gravitational fields, or spherically symmetric geometries. So nothing happens in the theta phi directions, so we just forget about them and look at the RT plane. So every point on this two-dimensional diagram is actually to be thought of as a two-sphere. And the straight line on the left is then the origin, and okay. And now, because Einstein's theory is generally covariant, you have a lot of freedom in defining your coordinates. So you define coordinates which are spherically symmetric, but you redefine them in such a way that on this diagram, light rays are always going to propagate at 45 degrees. Okay. You do something more, which is, in principle, you're defining, you're going to be talking about processes in infinitely large space-time, which of course I cannot draw. So I want to bring infinity to a finite distance, and this I do by some sort of singular coordinate transformation. So suppose r going to 1 over r will bring infinity to 0, something similar over here. And since the structure is richer, you essentially, for the purposes of my talk, have two interesting infinities to look at. One infinity is the place where all null rays emanate from in the distant infinite past, and that is this represented by this line here. And the other is where all null rays in the space-time end in the infinite future, and that is represented by this. For some reason, I think Penrose decided to call this, label these things. He decided to denote them by script I. And nowadays, and I think he himself, just shortened it and called it scry. So whenever you say scry, scry is just scripti, which is just this null infinity. So you have scry plus, which is the future one, and scry minus, which is the past one. Okay, so now in this diagram, this is depicting some matter which is collapsing. So that always goes on, say, time-like trajectories. And this curly line is the singularity where all the matter ends up. And here's the definition of a black hole. If I go and sit at scry plus and I look into the space-time and I don't see all of the space-time, I have a black hole. Okay? So here you can see that you don't see all the space-time. This is there's a black hole region over here. And the last set of rays which come out to you are called the event horizon. So this is exactly the same, just a different representation of what you've seen before. It's important that this scry plus be infinitely long. In other words, it's geodesically complete. And otherwise, you may not actually have a black hole. So I can come up with fake examples. So you just take flat space-time and you cut off some part of flat space-time, some infinitely large wedge over here, you cut it off. Then you go and sit on this scry plus, which is where all the null rays in this flat space-time come and sit, and you look back, and of course you don't see this part, but it's just flat space-time. And the reason, and so even as you know, strong electric fields, etc., will create particles, oppositely charged pairs, etc. Strong gravitational fields, which are time dependent, can also create particles. And a black hole situation is an example of a time varying gravitational field. So the gravitational field is varying because there's collapse happening, and then here it's kind of flat. As you go here, the field changes, etc., etc. So in time there's a variation, and this leads to particle production. And this particle production is really what the Hawking radiation is. But Hawking does a much more detailed analysis, and his conclusions are that particle production in a collapsing black hole geometry is has got a very universal kind of nature. It's thermal, as we have heard in Paddy's talk. Right? So Hawking's result says that a black hole radiates thermally. And of course, the stronger the gravitational field, the more it would radiate. And it turns out that the temperature of this black hole is inversely proportional to the mass. Also turns out larger is the mass, if you go near the horizon of the black hole, smaller is the curvature. So you expect some sort of inverse relationship anyway. So large black holes radiate very slowly. Small black holes have much more curvature at the horizon, they radiate faster. So the temperature of a black hole is written over here in terms of Planck mass, etc., etc. And so if you have a solar mass black hole, then its temperature is very, very low. It's 10 to the minus 8. So you need much, much smaller black holes to have some reasonable temperature. And in fact, the evaporation process is so slow, it's I think many times larger than the order of the lifetime of the universe for even a solar black hole. And I think if you put the numbers in, if you want to have a black hole at the beginning of the universe, which is now sort of significantly evaporated down, it has to have the mass of I don't know, someone told me a typical mountain or something. Okay, so the point is that once a black hole radiates, it loses mass. And once it loses mass, this thing becomes smaller, so its temperature grows. And the hotter it gets, so it's an unstable process. It has negative specific heat. And the black hole mass starts shrinking, but the process is very slow until the black hole becomes, of the order of the Planck mass or more, around the Planck mass. Of course, when it does that, then one expects quantum gravity fluctuations also to take over. So even the quantum fields on a fixed geometry approximation breaks down. But it's the paradox which I'm going to come to tell you is already sort of in play, because what has happened in this evaporation process is, since it's so slow, you just can approximate it by one parameter family, say, of Schwarzschild black holes with ever decreasing mass. And this is the Penrose diagram which Hawking drew. So you have collapsing matter, Hawking radiation coming out, the strength of this singularity decreases as you go from left to right, and then at the end you have some Planck mass sized black hole, and you have a whole bunch of thermal radiation. And basically this is a mixed state, because the thermal radiation just far, the entropy of that far outnumbers that of this Planck mass black hole. And in fact, if you demand that there are enough correlations in this Planck size object, it has to have huge number of correlations with the radiation for the state to actually be pure. And then it has to have a huge number of internal states, but this is ruled out by some effective field theory arguments. So basically the point is that if you started out with a matter in a pure state which collapsed to form a black hole, the end point of evaporation is just a whole bunch of thermal radiation. And you start off with a pure state, you end up with a mixed state or a density matrix. And as we heard in the last talk, quantum mechanics does not allow it. And this is the point of tension. So you've taken normal quantum field theory, gravity, put them together in a robust approximation, and then you are led to this paradox that there's somehow you've lost unitarity. Okay, so now let me come to an alternate view of the process. And from this diagram, you can see that it's not strictly true that what you have is a bunch of radiation and a Planck mass object. You also have a boundary to space-time. And just naively, I mean, it seems that, you know, what happens is that lots of stuff falls into this boundary, and it's a singularity, it just ends there, and that's why all the information is gone. So what Ashtekar and Bojewald do is they say, well, what happens if we have a quantum theory of gravity? A quantum theory of gravity is not only going to have effects at this point, but it's going to have effects all along this singularity, right? Because that's where the gravitational field is infinite. And so you definitely expect quantum gravity effects over there. And if your quantum theory of gravity resolves singularities, then you can go beyond this singular region. And so they propose the following diagram, which is a kind of Penrose diagram. So this is this singularity which has now been replaced by a quantum region. But evolution of operators and sort of wave functions and so on is still fine. So one could imagine a scenario where after some time this region again classicalizes, and so you have a much larger space-time in some sense than you thought you'd started off with. And again, you have collapsing matter. Hawking's argument is very robust, so there's lots of radiation, thermal radiation which comes out. But then if you're long enough lived, if you live very, very long, you will be able to see correlations coming out from this quantum region, and which restore purity of the state. Incidentally, it turns out also for other reasons, I think, which Abhay mentioned in his talk, public talk, the event horizon is not such a useful concept once this hole starts to radiate. And what is more useful is this concept of a dynamical horizon, which is more quasi-local. It consists of outer marginally trapped surfaces. And the dynamical horizon is like an apparent horizon initially. Then once it starts radiating, it almost looks as if it's going to asymptote to an event horizon, but then it turns around and becomes time-like, because once you take, it just happens that there's a balance equation which you can derive just in classical theory. If you go on radiating from a dynamical horizon, it has to come and become time-like. So there's a qualitative change even in the fact that you no longer have an event horizon. Okay, so this is one possible resolution, but it's of course very, very qualitative. I just sort of drew some diagrams and did this and that. So one would like to bring some, see whether, you know, in a more quantitative setting, one can do something, and so that's what I'll turn to next. And the quantitative setting is that of a model of two-dimensional black holes. So it goes by the name of the Callan, Giddings, Harvey, Strominger model. So these people, I think in the early 90s or late 80s, this is a string-inspired model, but I'm going to forget all its string antecedents and just look at this as an interesting two-dimensional field theory. And as I'll show you, it contains black holes in its solution space, and then it has the paradoxes which I've been talking about. But because it's simpler, it's more amenable to at least some attempts at quantization. So this is the model. Let me just describe it. So it depends, there's a part which depends on a two-dimensional metric, or minus plus signature, and another scalar field which I'll call the dilaton. And then there is some matter. And the key point which makes everything much, much simpler is that this matter field is conformally coupled to the metric. So in effect, what it sees is just the conformal class of the metric. And since in two dimensions, you know, all metrics are conformally flat with trivial topology, this really is, there's some sort of flat space-time dynamics underlying the whole thing which encourages the solvability of the model. Okay, the coupling constants of the theory, I haven't written them down because they're all over here. There's a two-dimensional Newton's constant, which has dimensions of inverse Planck's constant. And then there is something which people sometimes call a cosmological constant, because it has dimensions of length inverse. As I said, the metric is conformally flat, and I'll call the flat just fixed coordinates, gauge fix the diffeomorphism freedom, and call this flat metric eta. And eta has some inertial coordinates t and z, and it's convenient because I'm going to be talking about these massless scalar fields to look at null coordinates. So these are light cone coordinate z plus minus. And then the equations of motion for the scalar field, as I said, the scalar field doesn't see this omega at all. It only sees the flat part. And the scalar field satisfies the flat space-time wave equation. And so always get this wrong, it's a sum of left movers, which are these plus guys, and right movers, which are these minus guys. Turns out that the remaining equations can be solved for the other fields, namely the metric, which is basically this omega, and the dilaton field, in terms of the stress energy tensor of F. So really the true degrees of freedom of this model are F plus and F minus. Now this model, as I said, has black hole solutions, so let me come to that. So if you switch off the right moving data and give only left moving data on Scry. Okay, so before that I have to tell you that we are in 2 dimensions now, so it's not spherical symmetry in 4 dimensions, but we're actually in 2 dimensions. So we have a left and a right infinity. You have a left null infinity, right null infinity, future and past. And you can prescribe data here, which is just trivial, and data here, which is non-trivial. And what you find is that the solution for omega is such that the geometry is then that of a black hole, in the sense that this matter goes, it forms a singularity over here. And if you go at Scry plus right, and you look down upon the space-time, you're not going to see this bit. Furthermore, Scry plus right is complete. And so there is a black hole when you view it from the right. It also looks that there's a black hole when you view it from the left, because then you don't see this part. But if you go and see what happens, Scry plus left is actually not geodesically complete. So it's really not, you're not doing anything with black hole physics if you start messing around in this direction. So it's a model has its drawbacks, and this is one of them. You can now ask to do a Hawking-like calculation. So this was done by Giddings and Nelson. So you take this classical geometry and you investigate what happens to the propagation of a quantum conformally coupled test scalar field on this. So you put the test scalar field in its minus vacuum. Okay, you only consider the right moving modes, because that's where the black hole kind of behavior is there. So you take modes, you populate them with the vacuum over here, and then you can go up here and you can ask what you get, and what you get at late times is actually thermal radiation, and its temperature, unlike in the 4-dimensional case, is independent of mass, and it's given in terms of this cosmological constant kind of term kappa, so it's kappa h bar. But there is a Hawking paradox. It indefinitely radiates, and the same questions which I had asked initially can be posed over here, and we would like to understand them. For future reference, and this is quite important, the black hole space-time, it turns out, so occupies only a part of the z plus z minus plane. So this is z plus and this is z minus, and the full z plus z minus plane would be this, but then a singularity comes and cuts it out. And this is an important point which I'll get back to. It's just a remark at the moment. Okay. So now, unlike in full quantum gravity, one can at least make a decent attempt to write down a quantum theory. By no means does one have full control on the quantum theory. What rather one has is a quantum framework. What is under control is the quantum description of the true degrees of freedom. But the operators which are composite, corresponding to the geometry, etc., are not that much in control. But nevertheless, as I hope to convince you, even this framework is rich enough that you can learn something non-trivial about the information loss problem. So I do what one would sort of naturally do, since it satisfies this flat space-time equation on eta AB. I just quantize F as a free scalar field on this flat space-time on Fock spaces, which are a plus and a minus Fock space. And therefore the arena, the natural arena for quantum theory, is the full Minkowskian plane. So in the classical theory, you give me some data, it occupies some part of this Minkowskian plane. If you give me some other data, it might occupy a smaller or larger, it just depends where the singularity goes and cuts the thing. But you want all possible solutions, and the natural arena then is actually, as in quantum theory, is that of the full Minkowskian plane. And remember that f plus and f minus are the true degrees of freedom. So actually, we have just shoveled them into the matter, but really the Hilbert space is one for the entire model, the gravity dilaton matter model. It's just that the true degrees of freedom are parameterized by the scalar field here. So the dilaton and metric then are complicated composite operators on this Hilbert space, and they satisfy, at the moment, we have proposed equations, operator equations, but at the moment there is a aspect of formality in these equations, because as in classical theory, the dynamics of these operators is driven by the stress energy tensor of the scalar field. But even in the context of quantum fields on fixed curved space-time, in order to, you have to be quite careful in defining the stress energy tensor, because it contains products of fields at the same point. And you have to use the background geometry to separate these points and then bring them together again, take out the right infinities, and then you get the right answers. The stress energy tensor acquires a trace anomaly and it actively reacts to the curvature. Now here we have a quantum field, but on a quantum space-time, because the omega, the conformal factor, is an operator. And we don't know how to do quantum field theory on a quantum space-time. And what the stress energy tensor would be of the quantum field on this quantum space-time is an interesting question to explore in its own right, but we don't have any answers. And it will be some dependence on this conformal factor, but we really don't know, so the equations are not completely defined. Despite this, as I hope to convince you, this sort of limited framework itself allows some progress on this information loss problem. So this is the quantum sort of, this is the physical Hilbert space, and now what I have to do is to tell the theory that it has a black hole. So I have to take a state which corresponds to, as best as possible, to the classical black hole solution, which has this F going this way and no matter on this part of the space-time. And so what one does is one takes a quantum black hole state, which is modeled on this classical data. Right. So on the left, the classical data was trivial, so we put it in the vacuum state at scry minus left, at scry minus right. We had matter in fall, so we model a coherent state on this classical matter data over here, and this is the state which we will say is the analog of the black hole, which gives us a quantum black hole state. In this context, since the black hole stuff is all happening, this way, the information loss issue takes the form, what happens to the zero, this is the minus part, this is the plus part, this is scry plus right over here. So what happens to the 0 minus part of the state during black hole evaporation, and what happens when we look at that state over here at scry plus? So that is, typically one would expect information is going to be lost because of this thermal Hawking radiation, purity of the state is not going to be there, you're going to have a mixed state, etc., etc. So what happens? This is the information loss problem in this context. Okay, so what we shall do is we'll extract physics from these slightly formal operator equations using some different approximations and ansatz. Okay, so that is the way to proceed, and they are going to be of two types. The first one is just to say, do something which is actually blatantly wrong, but just go ahead and do it anyway. So we take a trial solution to these operator equations, but for that we need to define the operator equations better, and so we need to define the stress energy tensor operator, and we simply normal order it once and for all with respect to the structure of the flat fiducial Minkowski spacetime. This is the wrong thing to do, because actually we are not taking into account the geometry, neither classical nor quantum, of this black hole solution. But nevertheless, let us do it and proceed and see what one gets. So what one will hope to learn is issues which are not that much related to back reaction physics, where the stress energy tensor depends on the curvature, but rather some conceptual lessons which come from an underlying quantum gravity perspective. After that, what I'll do is I'll look at another approximation where I simply take expectation values of various operators, throw away the ones which have gravity dilaton fluctuation. I throw away all the gravity dilaton fluctuations but keep the matter ones, and this is exactly the analog of semi-classical gravity, TAB, GAB driven by expectation value of TAB. So I'll do these two things and see what one can learn from there. Bal, how much time do I have? Okay, yes, I'm well. Okay, so let me first use this flat fiducial flat metric and define TAB. It just means I normal order it with, you know, with respect to the annihilation creation operators at scri minus. Then automatically, I mean, there is no trace anomaly. One can actually solve the operator equations explicitly. So I can give you almost operator valued distributions for omega hat, and for omega hat remembers the conformal factor operator and then the dilaton operator and so on, in terms of the stress energy tensor of this free scalar field, which I know how to write down. And so it so happens that if I have this solution omega hat, and I can take its expectation value in this black hole state, and what I get is exactly the classical solution by the infall, which I had written down a Penrose diagram for. And on the singularity, it turns out that this is the conformal factor in the classical theory vanishes, and on the singularity, therefore, in quantum theory, its expectation value vanishes. But there's nothing wrong with omega hat. It's still a completely well-defined operator. In fact, it's defined everywhere on the Minkowskian plane. Now, near this classical singularity, certain physically relevant operators, which are related to quasi-local energy, have ever increasing large fluctuations as you go closer and closer to the singularity. So this is again a domain where one would not really trust the expectation values. Nevertheless, as I said, omega hat is defined on the full Minkowskian plane, even so to speak above where the classical singularity would be. And this is the first hint that one is seeing a quantum extension of classical spacetime. So I'm just drawing here the mean geometry. This is exactly the same as the classical geometry over here, below the singularity, but the omega hat expectation value is perfectly well defined above, and there is this extension over here. Of course, I mean, since we've used a very bad choice for the stress energy operator, there are, you know, this is not a very physical thing upstairs, but anyway, the point is that there's an extension. What about the Hawking effect? Can one say anything about the Hawking effect? It turns out that one can, and what one can do is one can take the quantum black hole state, one can compute the expectation value geometry, which is what I've plotted over here. One can look at the 0 minus part of this state and ask how it is interpreted by freely falling observers of this expectation value geometry out at scri plus. Okay. So remember, this is not a test field anymore. This is part of the quantum black hole state. And if you go over here, it turns out that computationally it's identical to the Hawking calculation, and what you see over here is the flux of particles at a temperature which is independent of the mass. Now, because this eta AB is just there, it's not reacting to the geometry at all, and we've used it to regulate the stress energy tensor, there is no back reaction of this radiation. So you have classical matter field, it curves the space-time, collapses, forms a black hole. The time varying gravitational field then causes particle production, and then of course you would expect that this added particle production stress energy tensor would back react and cause curvature on the metric, and so there would be corrected equations. And of course this is completely absent because of the choice, the inadequate physical choice we've made. So one would like to include effects of this back reaction. So the takeaway lesson from here is that, well, there's an extension to space-time, and expectation values and classical constructs are not to be really trusted near the singularity. So that was what this thing taught us. So now we do what we call the mean field approximation, which is really semi-classical gravity. So take the expectation value of these equations with respect to the state, neglect fluctuations of the gravity dilaton sector, but not of the matter sector, and you get the exact analog of semi-classical gravity equations in 4 dimensions. Is that, the Einstein tensor is equal to the expectation value of the stress energy tensor. The stress energy tensor has a classical part and some order h bar part which depends on the geometry. Okay, and then so basically it's a kind of a triplet. There's a state, there are operators, and there is a geometry, and everything has to go consistently. So the expectation value of the stress energy itself depends on the geometry. On the right hand side you have the geometry. This is what happens in 4 dimensions. It is also exactly the same structure in 2 dimensions over here. But once one puts this back reaction in, you lose solvability. So analytic, it's not really amenable much to analytic work. One can extract certain features of the geometry, and this was done by Susskind and Thorlacius in the 90s. And then there were attempts to numerically see what happens to these equations by Piran, Strominger, and Lowe. And what they found was basically this thing. So what they could deal with best was just a matter pulse which went and fell in. So these are now the mean field equations. They're modified from the classical CGHS equations. And what one found was, so this part before the matter pulse comes is flat. You still have a singularity even in the mean field theory. And the singularity is a bit funny. What happens is that it ends somewhere within the space-time. And you develop here a Cauchy horizon, because this is in the causal, what is over here is in the causal shadow of the singularity. So your numerical code, etc., breaks down over here. So you have a last ray. You also find that you have a dynamical horizon exactly of the type in the AB paradigm, which arises over here. Now, as I'll say later, these simulations actually, turns out, today, looking back, are in sort of a very, very bad part of parameter space where the mass is too low. And also the methods, of course, were not that developed, and the simulations really couldn't say what happened near the last ray. In any case, while one will not trust the mean field theory in the vicinity of the singularity, because this is precisely where one expects quantum gravity and dilaton fluctuations to be large, one should be able to trust mean field theory when space-time is benign and asymptotically flat somewhere over here. So this leads to the next step in the analysis, which is another approximation called asymptotic analysis, where I sit on Scri plus over here and I expand out various fields because one is at asymptotia, infinitely far away, so it's close to a flat solution, etc. And then I get certain equations from the mean field equations, and these equations need some boundary conditions, and these boundary conditions are provided by our knowledge of the underlying quantum state of the system, which is this black hole system, which is this black hole state. So it turns out, I mean, I'm not spelling this in detail, so I don't expect you to completely understand, but there are certain boundary conditions which come from the fact that we know what the quantum state is of the true degrees of freedom, and that, coupled with the equations at asymptotia, dictate very strongly the response of the asymptotic geometry to the energy flux at Scri plus right. And if you analyze these equations, it turns out that if you assume that this radiation which is coming out at Scri plus right of the physical spacetime, not this Minkowskian fiducial spacetime, if it it stops, because at some stage that's reasonable. One would assume that it goes on evaporating, and at some stage it stabilizes and it stops. The little bit of a strong assumption is that it stops smoothly and is kind of compact support on Scri plus right. If you do this, then it turns out, just from this asymptotic analysis, that the Scri plus right of the mean field spacetime is exactly as long as the Scri plus right of this fiducial spacetime. Okay, so what this asymptotic analysis, together with this knowledge of this quantum state, is trying to tell us is that, again, the null infinity of the physical spacetime, classical spacetime, is now even the mean field spacetime. Well, the classical spacetime is extended. And there is again a quantum kind of extension, which you already see in the asymptotic analysis of the mean field equations. Not only that, if this happens, one can show that the vacuum state which we started off with, when looked at with the eyes of freely falling observers at Scri plus right, it's a state full of particles, but it's a normalized pure state. Okay? So there is no, in that sense, in the sense in which I posed the initial question, the analysis is indicative of a picture in which there is no information loss. And the picture, again, is the following. So of course here we don't know, we don't have the full quantum theory, but one believes that there is, from the first analysis where I just took normal ordering, that there is some way to go over the singularity. In fact, Amos Ori has done in further analysis with some approximations, etc. But in any case, suppose we say that the singularity is resolved, then we have these bits of information. We have, this is just analytically, you can show it's flat before the support on the matter. Matter goes in. In this part, one has the numerical analysis of the mean field equations. In this part, in a vicinity of Scri plus, one does asymptotic analysis, and one puts all these different things together, and the picture one has is basically that there is singularity resolution here, a dynamical horizon comes over here and evaporates, and the Scri plus is much larger than the Scri plus of the classical space-time, and therefore that there is really no tracing out of any modes, nothing is lost, all the information is reproduced over here, and that can be rigorously shown once one assumes that the asymptotic analysis and this flux vanishing condition is true. So the conceptual underpinnings of this diagram, as I mean, so just to summarize, the interior to the past of this singular region is given by mean field numerics. Near Scri plus right, we have asymptotic analysis, and the conceptual underpinnings of the whole story provided by these operator equations suggest singularity resolution and an extension of classical space-time. The vacuum state is then a pure state. It's populated with particles in this Hilbert space of Scri plus right. And then information emerges between, as correlations between the stuff which is, I'm sorry, yeah. So because of this extension, information emerges between correlations at early times and at late times. Of course, what one would like to know is how fast does the information come out, and that actually is a difficult question to answer. So there's no energy flux if the assumptions are true. There's no energy flux over here, and so one would think maybe that all the information comes out whenever the energy flux stops. It's just flat space-time, and then all the information comes out there. But one cannot make a very strong statement, and this really has to do with the definition of information in quantum field theory. And I think there will be a talk on entanglement, etc. And there is a real problem in trying to define information because of these tails. You cannot localize particles in quantum field theory, and so what do you mean about tracing over degrees of freedom at a certain point? It's not very clear. You have to make some approximations, but then the answers you get are going to depend on what you feed in, and it's a little bit of a hairy issue as to what exactly information means. What one can unambiguously say is that the state is pure, and that is a completely unambiguous statement. But one would like to formulate this problem and ask, how fast does it come out, because it impinges on the issues of remnants and other things in 4 dimensions. Okay, so that basically is more or less the end of my talk, except that I just wanted to tell you about some recent things which I have not, I could not be involved in because they involve really hardcore numerical simulations. So we have this picture, and the question is there possible supporting evidence somewhere, additional supporting evidence? And one thing to do is to ask questions of the mean field theory itself. I told you had numerical simulations. And one question one could ask is, well, if this space-time is going to be, extending beyond this, can one ask at least in the mean field theory, whether this is geodesically complete or whether it just stops over here? Another question one can ask is, well, is this singularity going to propagate all the way out over here, or is the curvature in the vicinity of this last ray actually non-singular? And these are very, very hard questions to answer numerically. And it was simply, there was a lot of controversy in these earlier works. In fact, even Hawking and a student tried to address this. They all got different conclusions because I think the numerical methods were not sufficiently developed then. But now one has these state-of-the-art numerical simulations using things which I have no idea about. They're called adaptive mesh refinement, etc., which enables them to get, sort of factors of, I don't know, 10 to the 19 precision, over here, right near the last ray, and they have to go really, 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 really close in Z plus Z minus to the last ray, and run lots of simulations and do lots of work. But then the final result is really, really beautiful and wonderful, that this Scri plus right actually turns out unambiguously not to be complete. Okay? So it's begging for an extension to happen, Moreover, the curvature around the last ray is not diverging. Okay, so these are both, I think, positive inputs for the picture of which I had sketched in the earlier part. There are other very interesting numerical things which have to do with possible universalities in the evaporation process, and maybe even possible critical behavior, critical scaling and so on. But those are really numerical things, and whether they they can also find similar things in the mean field equation, 4 dimensions, etc., is an interesting question. Okay, so let me summarize and conclude. I'm done. So the basic message I want to give you is that in this context of 2-dimensional black holes, combination of ideas from non-perturbative quantization, mean field approximation and numerics there, and asymptotic analysis point to a unitary picture of black hole evaporation with the following key features. It has singularity resolution, there is an extension of classical space-time. The last thing I don't want to dwell on, because this has to do with these issues of fluctuations and tails and so on, so they always quantum fluctuate. This has to do something with the definition information, which I will not get onto over here. And just as a note, the consistency of the mean field approximation requires a large number of scalar fields, a large n, but this can be taken care of. And finally, this CGHS work was done with Abhay and with a student of his who is now a postdoc in LSU. His name is Victor Tavera. So I think I'll conclude now. Thanks.
I don't really need a mic at this distance, but maybe, yeah, okay. I have a couple of comments and a question which is slightly aside from, taking you a bit aside from what you have talked about. It is known that not only in 1+1, but even in 4 dimension, if you just stick to the conformal degree of freedom, which is a free scalar field, and you quantize it, you achieve the first two. The singularity resolution does take place.
I see.
And the expectation value vanishes, but the fluctuations around it allow you to extend the classical space.
So what is the field coupling? I mean, how do you
omega I plus 1/6 r omega square is
that conformal.
Absolutely. So you just take the conformal degree of freedom, freeze all other degrees of freedom, and you do it in 4D. Now the reason this was, while we did this for cosmology, where all these things was done, but never for black holes, is because I had this serious moral problem that whether non-conformal degrees of freedom are going to play a role in black holes or not. And if you do any kind of rough analysis, you end up knowing that the non-conformal degrees of freedom are vital. Therefore, how far will you trust a model which has only conformal degree of freedom, which is the 1+1 CGHS model, and to make comments about what is eventually going to happen in a real 4-dimensional thing? That is one worry which I have.
Yeah.
The one more thing is the...
I'll probably forget the second question by the time I answer the first one, so you can ask it later. Yeah, I mean, it's really a question of what your intuition is and what you take away from toy models. So it's absolutely true that the reason one could solve this model was because you had this conformal coupling. But I think, I mean, my own feeling is that the sort of lessons one gains in terms of what can happen and the sort of level of detailed calculations which bear the intuition out. I mean, it needn't have happened. I mean, this sort of mean field numerics might have just stopped. There might have been a singularity propagating, or a lot of things could have gone on. None of this happens. So that leads me to a certain faith in the fact that once you put in the back reaction, then it's no longer this simple theory. It's not this.
Well, we will come to back reaction later.
No, but that is
superposition principle. Once you put TAV expectation value on the right.
But that is an approximation. That is an approximation in the context of a particular black hole state.
But that is where the results were obtained, right?
Absolutely.
So I'm not very sure.
But that doesn't violate the superposition principle. I mean, you could give me a superposition of 2 black hole states. Right. I could superpose them, and then I would get a different set of initial conditions for the mean field equations.
Okay, let us not get into that.
So anyway, the point is that I think that there are robust lessons in terms of these extensions of space-time, etc. And already I think they are feeding into at least a picture of how one could bypass the standard objections to to scenarios where information is recovered. Okay, so there are a bunch of them, right? I mean, there are these standard arguments which, you know, is either bleaching or the fact that you know, you might have remnants, or you know, arguments against how things could all come out in the Hawking radiation.
I believe they are all straw man which can be easily knocked over.
And I don't think they can be easily knocked over.
No, the point
I don't think they can be easily knocked over.
Okay,
And I think the point is that, you know, what this allows us to do is to refine our intuition sufficiently and give sufficiently careful rebuttals to what you know, to what could have gone wrong in the 4-dimensional case. But again, this is a subjective kind of thing. So I mean, I think I learned a lot, but you know, other people may think not.
I need to make a couple of comments on that. The reason I called it straw man is that we all understand that information loss, the crucial thing is not event horizon but singularity.
No, this is not a commonly accepted view.
That is correct, but that is because of some misunderstood notions in the
we may say so, but yeah.
Right? So the moment singularity is resolved, information loss most likely will get resolved itself. So the thing to attack on is singularity resolution. But this is a welcome statement, but this would mean that in 4D, if I do just the conformal degree of freedom and I do a quantum theory on a black hole spacetime, and I find that the singularity is resolved, you would consider it as a very positive step forward, because it's a completely doable calculation and I can predict exactly the same thing.
Except that I'm not sure, okay, we'll have to get into the details. I do not know how well motivated this coupling is, right? Is it,
well,
because are you gauge
R root minus G.
Okay, so we should look at it. Okay,
you just take R root minus G, write it as omega square GAV and write it down, you get omega I minus plus 1/6 R omega square. Nothing else is involved. You are just confining yourself to the conformal degree of freedom of a 4-dimensional matrix, writing down an effective action for that, and you are quantizing it. You will find singularities are removed. It is established in cosmology, and to the extent Friedman interior is a dust solution of cosmology of the black hole, the same thing will go.
Okay, so we can look at it.
I think there are too many people asking questions, so maybe we should keep up.
Yeah. Yeah.
So did they assume anything near close to the singularity, or they assume that if it is 1 by r, it is 1 by r plus x or delta, or what is?
No, I don't think so. I think they just took the equations, and you have initial data at scri minus and scri plus, and you can propagate them in this direction. And I mean, you have equations which are completely well posed, and you just, of course, you cannot do anything beyond the last ray, because then you're in the causal shadow of the thing. There's a Cauchy horizon there. But you want to see the diagram? Yeah. So over here, I mean, you give data here and data here, and basically, I mean, you can propagate the data here all the way up, very, very close to what happens over here. And there is no, I mean, there are no assumptions. I mean, you have well-posed equations, and you have you have data, and you just evolve them over here. Yeah.
You get everything finite, stress energy is positive, but when you do a 4D calculation, then it becomes a negative stress energy tensor. So then people didn't know what to do it actually. This is in late 90s, early 2000s.
Sorry, what stress energy?
2D calculation, CGHS model,
yeah.
Whatever they obtained,
yeah.
Stress energy tensor,
yeah.
And then extended to the 4D calculation. Yeah. And like what Paddy was telling, and then you calculate stress energy tensor, but then the stress energy tensor turns out to be negative.
So
the Balbin out calculation.
Okay, I mean, the stress energy tensor is, at some places in this space-time it is negative. I mean, otherwise you won't get area decrease. So that's not by itself a problem, but it touches on another related and quite an interesting issue. So you see, what happens here is that typically what people were doing for the Bondi flux, the Bondi mass over here, they were identifying it with the stress energy tensor itself. Okay. Now, if one looks at what happens to the stress energy tensor and how it evolves, it gives a certain definition of Bondi mass for the spacetime. If you identify the stress energy of the scalar field at scri plus with the Bondi flux, and if you look at the simulations, now it turns out for completely independent reasons that what we did in our work, due to some completely different reasons, suggested a quantum corrected Bondi flux definition. Okay, so we just had it. Then the numerical simulations came along, and it turns out that, you know, by the time you get here, the traditional Bondi mass, depending on the data, can go on, it actually touches 0 and then it starts going below 0. But this new quantum corrected Bondi mass which one defines, almost miraculously there is a kind of universality. So if you have macroscopic size black holes, they all end up with you know, a sort of what is the remaining mass in the space-time is always something like, I think, 0.86 Planck masses with this new Bondi flux, if you define the Bondi mass that way. So they also definitely, I mean, it's all there are also issues. So the stress energy tensor can be negative. I mean, I'm not saying that it is a negative over here in Scri plus, but it can be negative elsewhere. But there's also an issue about what you would consider as the quasi-local energy of the system. So anyway, this was just an aside. It was not directly in answer to your comment.
Yeah, I just had a curiosity. Did you make the statement that over that last ray,
Yes.
the curvature is finite?
Yes.
Or?
Yes. Yes.
So, and that is the Cauchy horizon, is that right?
That is a Cauchy horizon because there is a singularity of the mean field theory
Fine,
here,
I
and
see.
we can't
so,
do one.
So in some sense, it's a stable Cauchy horizon because the curvature, you know, is going.
Yeah, it is finite. Now I don't know about. I think they've
Okay.
just barely been able to compute, you know, this. But yeah, I think that would say it's basically stable, right?
Yeah. Okay. And
Right.
this is
Because there's a large amount of initial data which they have looked at, and that initial data is close to. Yeah, so it would basically say that this guy is.
So I
is
just
correct.
wanted to check
Yeah.
that. Thank you.
Yeah. Yeah, the question is okay. Yeah, go ahead.
How can you ensure that a pure state is a finite norm state in the Fock space?
Yeah, so this was not ensured. This is what comes out. One can show that the state you get in the out Fock space once you have the extended space-time in this particular example is actually a normalized finite norm state. So it's something you go and compute, and you can check that that is true. There are horizons, right? I mean, in the classical theory, there are horizons. In the quantum theory, there are these dynamical horizons. Oh, are you worried about how to define dynamical horizons in 2 dimensions? Is that the question, or what?
Is there an actual standard event horizon in this problem?
There is an event horizon in the classical theory.
You see.
Yeah, and there is kind of an event horizon. I mean, there's this last ray, which the Cauchy horizon. You can call it what you want in this mean field theory, but of course, in the final theory, one doesn't have real.
So this is different from the Witten black hole, which is.
In the classical theory, there are event horizons, right? Those are exactly. I mean, that's what I said right in the beginning, that there is an event horizon when you look at it from the right, right? So that dotted line is an event horizon.
One more question is, there are no degrees of freedom in gravitational field in 2D.
Depends where you put them. The 2 degrees of freedom are there. They are infinite. It's an infinite dimensional space of 2 degrees of freedom. I've just shoveled it into the matter field. The gravity, the gravitational field is determined completely by the matter field.
But it's like 2-dimensional electrodynamics, where there are no degrees of freedom.
No. Why do you say that?
Yeah.
There are no free propagating degrees of freedom.
In 2D.
No, well, that's not.
There is no gravity.
It depends where you put it, right? I mean, I've just presented you the. Sure. That I agree.
There is no graviton in 2D.
There's no. Well, yeah. Once you take away the matter, then you get just a static solution.
This is very much like the Schwinger model, which is also exactly soluble in 2D.
I see.
But it completely changes in 4D. This is his point. Okay? Then I want to ask some other question. We had Bob Wald here, and he was very definite. And
yeah, Sham told me that.
Okay,
yeah.
That the information loss is a fake problem, because the problem is arising because you don't have a global foliation because of the singular by. So it's not it's a fake problem because you cannot do quantum theory with a Hamiltonian, but you can do something else, local C-star algebras.
It
There is
depends,
no
right? I
problem,
mean, you can, I mean, his view would simply be that it's a traditional GR view that information is simply lost. There's singularity and that information is lost.
Yes,
This
but
is the
his-
traditional view.
There is
I
a
mean,
traditional view.
in the relativity community, a lot of people used to think that, in fact, Hawking himself for a long time, and then other people would think, and I think that is, from what I understand, Shyam telling me, is that is what is also Bob Wald's
Bob
point
Wald
of view.
was very clear that there is no contradiction with quantum theory because it is simply not globally hyperbolic when you remove the line. You cannot write.
Well, the question is what replaces it then, right? And I'm
local system algebras. He showed it.
I don't know.
Then
We'll have to talk. Okay, I don't understand.
Any more questions? All right. If not, we will be